Spaghetti bridges. Bridges come in a variety of designs, each having their own strengths and weaknesses. A better understanding of compression strength of load distribution of a truss bridge design began with researching different truss designs and experimentation using number 3 spaghetti. Through this project, a wide variation of bridge designs was looked upon, including camelback truss, bowstring bridge, wire truss, and Pratt truss. In the group of 4, we were required to build a bridge to withstand the most load using number 3 spaghetti and Sally's superglue to keep it all together. Through research, we were required to choose a suitable design for this project. The truss spaghetti bridge design needed to be equal or larger than 350 mm long and 80 mm wide. Two tests were taken in place, which included the practice bridge and an improved final bridge. We also needed to take into consideration of tension and compression of the load that is applied to the joints of the truss. Camelback truss. A camelback truss contains a polygonal upper chord with 5 slopes, uses a combination of truss and arc designs to maintain strength while spanning longer distances. A camelback truss design can span long distances, requires less materials to construct, and is able to evenly distribute tensile and compressive loads throughout the beams. Camelback truss designs can be complex to construct while also being heavier. Bowstring/arc. The arcs on a bowstring bridge uses a pin connection to help with horizontal force using the foundation. This means that the bridge requires a strong foundation like rock to work well with. This type of arc bridge is called a thrusted arc bridge. However, not all locations have strong bearings, so an alternate solution must happen. This is called a tied arc, where one side is a pin connection while the other is a roller connection. This helps alleviate the horizontal force. The arc of the bridge is strong against compression due to the curvature of the arcs, while the truss and beams resist the tensile force of the load. A Warren truss design utilizes equilateral triangles to carry the loads, with some members being able to work in both tension and compression. When acted upon by a live load, members toward the center of the bridge can switch from compression to tension. The use of the triangles increases the strength of a Warren truss design while requiring less building materials. Warren truss bridges spanning greater distances have experienced deflection flaws. The Pratt truss is a truss structure that is used over the past 2 centuries due to its cost-effective structure design. It is a simple design that has vertical members with parallel chords which are in compression and diagonal members in each panel which are in tension. The more efficient members reduce the self-weight of the truss bridge and eases the constructability of the structure. A Pratt truss is at a disadvantage if the load is not vertical. For the construction of our bridge, we focus on looking at truss bridges as their design allows the structure to withstand heavy vertical loads while maintaining a reasonable weight. Truss bridges can be built large distance if the design has the support columns necessary to support the design. We started off with a Warren design bridge, but soon after switched to the camelback truss as the design can distribute forces more evenly with the extra members. This is the hand-drawn design of our bridge, a camelback truss. These were the dimensions we followed while constructing the spaghetti bridge. The cross sections were later removed to correct weight issues during the building phase.
From the designs researched, a Warren truss bridge design was chosen as most suitable. By using equilateral triangles, the loads acting on the bridge can be spread out while limiting the forces to only compression tension. As the members towards the center can switch from compression to tension, a Warren Truss design bridge is suitable for vertical center load. Number 3 spaghetti was used to construct the bridge, with seals typically being used to join them. To create stronger members, 5 pieces of spaghetti were glued together to create 1x5 pieces. The 1x5 pieces were then joined to make 4x5 pieces, which became the members for the bridge. The 4x5 beams produced a uniform shape which made joining members easier, as there's a larger surface area where glue could be applied. By using 4x5 pieces, sturdier members allowed for greater loads to be carried. The average length of spaghetti was around 250 millimeters in length. Therefore, the top chord, trusses, and spanning beams were cut to approximate length using scissors, then grinded using sandpaper to the length specified in the design. As the length of the bottom chord was greater than the length of the spaghetti available, two 4x5 180mm members were glued together at the center to create the required length of 360mm. Once the 4x5 members were constructed and cut to length, the bridge was assembled based on the design. The trusses were first assembled on top of glad wrap to prevent the trusses from sticking to the table. By assembling the trusses on the table first, the glue was given time to dry, allowing for the members to stick cohesively before the trusses were connected using the spanning beams. Once completed, the bridge was weighed using a scale and observed to be over the specified weight requirement by 3 grams. When testing the bridge with the weight loading apparatus, 2 complications arose. The bridge does not span the distance needed to freely rest on the roller supports, and the bridge was not wide enough to properly hold the loading plate. Despite this, books were used to test, as it was observed that the bridge could only withstand 1 gram before reaching failure. 2 factors were identified as the main reasons for failure: the assembling of the members and the bottom chord. When gluing the spanning beams to the connecting trusses, insufficient time was given for the glue to dry, which create weaker joints. In addition, some members were not created to high quality, which reduced the surface area where glue was applied to members. This also created weaker joints and contributed to an earlier loading failure. As the length of the bottom chord was greater than the length of spaghetti, 2 members needed to be joined by glue. Because of this, the connecting joints became a weak point in the beam.
Is it solid moving?
It is. I can see it. Oh my gosh,
Yeah, I can see it.
Okay. The glue.
Using the knowledge base of the testing bridge, we decided to change our design to a camelback design. This design had vertical beams that would support the bottom chord from snapping. Also, the top chord for this camelback design is curved concavely towards the bottom chord. This helps strengthen the compressive resistance on the top chord. The bottom and top chord were using the same dimensions as the first bridge, but the trusses were made to be smaller as they carry less load, and it would help reduce the weight. We started gluing the bottom chord of the bridge first, as that member needed to be lined up perfectly to be stable. We then started to lay out the members to help us visualize the structure when gluing each piece together. Some errors were discovered when attaching trusses with the top chord. Because of more joints in the bridge design, each member had to be attached accurately to the calculations. However, this was done by hand, and so we had many human errors when drying the glue. We held up each member by hand when drying the glue, and this made some of our angles wrong, which resulted into some members being slightly too short or too big. Our decision to fix this was to sand the slightly bigger members and do what we could with the shorter members. The final product rated to be 200 grams and felt stable. The bridge was slightly tilted to the right due to the gluing process, but there was nothing we could do after drying the glue.
Prior to the completion of our hand-drawn design, we began designing our bridge on two softwares, SpaceGas and Matrix 2D. Using SpaceGas, we designed a 3D model of our bridge for running analysis of the bridge's reactions to loads. However, this software proved to be complex, so we decided on using Matrix 2D to run our analysis. The bridge was designed according to our hand-drawn measurements and sat upon two Y roller supports. After placing negative 10 kilonewtons of downwards force at the center of the bridge, we then ran an analysis to study what members will be in either compression or tension. Further analysis shows us the joints that will be under the most stress and how the bridge will presumably buckle.
Three, 4, 5, 6, 7. That's not.
To be fair, that's
That's
your
not your
Oh,
structure.
that's not-
That's not your structure. Yeah, keep loading it up. 9, 10.
No, because it was still working.
Keep loading.
When I was in love.
Yeah.
Once completed, our bridge weighed 200 kilos, the maximum weight limit. Upon testing the bridge, a joint along the upper cord failed at 8 kilos. This prevented the force from spreading through the truss members, creating dead weight. The bridge eventually failed at 10 kilos. A member of the bottom cord snapped due to the structure buckling inwards. The way the bridge buckled during the final test was accurate in comparison to the results seen on Matrix 2D. To improve upon this design, we could have created more surface area at the joints by sanding the members more efficiently. The members themselves were quite thick, being 4x5 spaghetti. As a result, they were able to withstand a much greater force than the said joints. Overall, the bridge was a success. It buckled as anticipated, and the joints under the most stress appropriately failed first.